All right, so today we are going to talk about complex truth tables. Last time we showed you how to use truth tables in a real simple way, how to run two sets of values where you had one unknown statement letter. But now we are going to run them through as if we don't know any of the pre-assigned values of any of the statement letters. So the formula for your truth table size is going to be this. You need a number of rows equal to 2 to the n, where n is the number of statements in your well-formed formula. So here we have an A and a B in our statement, so we will need two rows. If we had an A, B, and C, we would need 8 rows. If we had an A, B, C, and D, we would need 16 rows. So as I warned you, this gets exponentially more complicated as we add a single letter. Now, we set it up. We set up A and B so that we run through all 4 possible combinations of values. The situation where both are true, where both are false, and where one each is true and false. When you calculate it out, the only one of the 4 values where the statement as a whole is true is valuation number 2, where A is false and B is true. You plug in false for the A, true for the B. The negation on the B switches the true to a false. The results is that you have false on both sides of the OR. The OR is false, and then the negation on the outside of the parentheses switches it to true. That is the only one of the 4 statement values where you get a true statement. So there's a few things that we can use this for. One very basic thing you can use it for is to distinguish between contingent, tautological, and self-contradictory statements. Most statements are contingent statements, which is to say that the statement value will be true on some values of the constituent letters and false on other values of the constituent letters. And most statements fit that description. However, there are 2 special kinds of statements, tautologies and self-contradictory statements. Tautologies are statements that are true regardless of the values of the constituent letters, because the statement is true on all possible values. A classic example is P or not P. If P is true, the left side of the OR statement is true, and the statement will therefore be true. But if P is false, then the right half of the OR statement is true, making the OR statement true, making it true. So the statement P or not P is always true, no matter what the value of P is. Because when you run it on both possible values, the statement's still true. Similarly, self-contradictory statements are false on all possible truth values. A standard example of a self-contradictory statement is both P and not P. Remember, an AND requires both halves to be true for the AND to be true. So when P is true, the not P on the right side of the AND is false, making the statement false. But when the P is false, the left side of the AND, the P, is false, and therefore the AND is false. So on all possible combinations of truth values for the constituent statement letters, the claim P and not P is always automatically false. So one thing you can do with a truth table is that you can run through all possible values of the constituent letters to distinguish between contingent, tautological, and self-contradictory statements. All right, so let's look at some from 6.5 exercises. All right, I'm going to do 2 of these for you, just to give you a sample. All right, looking at number 2, which is not P and Q. All right, so I have to set up the 2 constituent letters over here on the left. I'm going to need 4 rows because I have 2 to the second, which is 4. We're just going to alternate between true and false on the innermost value, and then we're going to double up on the next value, and then we're just going to calculate it out. Situation 1, P is false, negation makes it true, Q is false, that gives us false on 1/2 of the and, making the and false. Second valuation, P is false, gets negated to true. Q is true, gives us true on both sides of the and, makes it true. Third valuation, P is true, gets negated to false. The Q is false, the and is false on both sides, making it false. Fourth set of values, Q is true. P is true, but gets negated to false. We have false on 1/2 of an and, making it false. That's the truth table for it, and it is a contingent statement. Simple enough. Let's do something slightly more difficult. Let's do number 3. P or Q and not R. P or Q and not R. All right. So we'll start at the innermost parentheses. Q is, on the first set of values, Q is false. R is false, gets negated to true. We have an and that's false on the 1/2, making the and false. The P is also false, so both sides of that or are false. Second set of values. Q is false, makes this and false. P is still false, both sides of the or are false. Third set of values. Q is true, R is false, gets negated to true, makes it true on both sides of the and, which makes 1/2 of the or true, making it true. Fourth set of values. Q is true, R starts off as true but gets negated to false, makes this and false. P is still false, so both sides of the or are false. And then I'm going to do something that's a little bit of a shortcut. Look, the better you get at logic, the more adept you will get at spotting when you don't have to calculate absolutely everything out. So I see on these last 4 set of values, P is always true. I see the final operator in this statement is an or, and I only need 1/2 of an or to be true for the whole thing to be true. So I'm going to look at those 4 final statements and say, guess what? Those are all true just based on the P, no matter what goes on over here. Do you all see that? So I'm going to make my life easy. I'm just going to do that. I'm not going to calculate all this stuff out. That's like extra work, and I'm lazy. I don't want to do all that extra work. Now, don't just go off willy-nilly trying to do shortcuts unless you understand with 100% certitude that what you're doing is legitimate, which is why with these basic operators, you need to have them down absolutely cold. Because we're going to increasingly do problems where you have to calculate 8 or 16 or 24 or 32 sets of values very quickly. Questions? And this, like our other statement, is a contingent statement because it's true on some values and false on others. How do I know how to set this up over here? In a certain sense, what's important is this. You need to run through all possible logical combinations of the truth values of P, Q, and R. The easiest way to do that is to alternate the truth values of the innermost one. And it doesn't matter which order you put them in. As long as for one, you alternate it like this. For the next, you double up. And for the final one, you quadruple. I mean, so yeah, if you made it PR and Q, that would be fine too. The order, this would look a little different over here because this would change as these combinations change. But these are the only 8 possible combinations of truth values, no matter how you mix them up. You are welcome. So yeah, just as when translating, you can choose any letter to represent any statement. You can put this in any order you want. Just do it in an order that makes sense to you and makes it easy for you to remember. Anybody else? All right. Let's see. I did 2 and 3. I think these are pretty easy. Let me get some volunteers, and I want to see people do. I'm going to want to see people do 4, 5, and 6. Yeah. I'm going to want to see people do 4, 5, and 6 of our problems on 6.5. So who will do 4 for us? All right, come on up and do 4 for us. You can borrow my book if you need to. You and Sam. Who'll do 5 for us? Please, come on up. And who will do 6 for us? Give it a shot. Thank you. I don't know why my eraser doesn't work on this board. Yeah, go right ahead. You can use a different one if that one doesn't work. All right, looks good, looks good. All right, let's take a look at this. All right, so if if and only if P and then Q, then Q. We look at the innermost parentheses. On the first set of values, P and Q match. Therefore, you start off with true on the innermost parenthesis, which makes the left side of the arrow true. Q is false, however, which makes the arrow false because it's true on the left, false on the right. And that statement as a whole is false. Second set of values, P and Q do not match. That makes the left side of the arrow statement false, which makes the arrow statement true. Third set of values, P and Q don't match, makes the triple bar false, makes the left side of the arrow false, which makes the arrow true. Fourth set of values, P and Q. No big deal. Fourth set of values, P and Q do match, which makes the left side of the triple bar true, which makes the triple bar true, which makes the left side of the arrow true. But Q is also true. Therefore, both sides of the arrow are true, and the table is true. Very good. All right, let's look at this one over here. If both P and not Q, then R. We've set up the table properly. When they're all false, the Q gets negated to true, but the P is still false, which makes the and false. We have an arrow with a false left side, making it true. In fact, that's going to happen on all four of the first valuations. Anytime P is false, the and is false, which makes the left side of the arrow false, which makes the arrow true. So that makes the first four sets of values all true. On the fifth set of values, we have Q starts off as false but gets negated to true. Both halves of the and are true. The the R, however, is false. So we have true on the left, false on the right, and that appears to be the one of the 8 combinations where the arrow statement will be false. The sixth set of values, Q is false, gets negated to true. P is true, so both halves of the and are true. The R is also true, so we have an arrow with true on both sides, which makes the arrow true. Seventh set of valuations, the Q is true, gets negated to false, making the and false, making the left side of the arrow false, making the arrow true. And on the final set of values, the Q starts off as true, gets negated to false, makes the and false because it has a false on one half. That makes the left side of the arrow false, which makes the arrow true. All right, and we have P or not Q. If P or not Q, then R. That may not be exactly right. Let me take a look at this. All right, so we've got it set up properly. That's good. First set of values. Q starts off as negative, but it gets negated to a positive, makes the or positive, which makes the left side of the arrow positive, but the right side, the R is false. So it's a false arrow. Good. The second set of values, the Q again starts off as negative, gets negated to positive, it makes the or positive. But this time the R is also positive, so both sides of that arrow are positive, making the statement positive. On the third set of values, so now we start with the Q. This time the Q starts off as true, gets negated to false, and we have false on both sides of the or, because the P is false, the Q starts off as true but gets negated to false, the or is false. And because the or is false, that means the left side of the arrow is false, and that means the arrow, the whole statement is true. That will happen again for the fourth set of values. The Q starts off as true, gets negated to false. The P is false, makes both sides of the or false, which makes the arrow true. On the fifth valuation, P is true, makes the or true. The R, however, is false. So we have true on the left, false on the right. So it is false. On the the sixth set of values, again, the P is true, makes the or true, makes the left side of the arrow true. But the right side, the R is also true, so both sides are true, making them true. On the seventh set of values, P is true, makes the or true. The R is false, which makes the arrow false. And on the final set of valuations, again, it will be true because the P is true, making the or true, making the left side of the arrow true, while the right side is also true. All right. Questions? Whew. Yes, sir. Yeah, good catch. So, right, so if you were to look at this one and realize that that R is true on every other valuation, and anytime that R is true, the arrow has to be true, you could just start off by making valuations 2, 4, 6, and 8 true. So you can do that. All right, are there any of these other exercises that you'd like to see me do, or can we move on to the next, to 6.6? All right, looks like people have a reasonably good grasp on things. All right, so here's what we've been pushing towards. We don't want, the final goal of the truth tables isn't that we just want to test individual statements to track their truth values. What we want to do is we actually want to be able to test entire arguments for valid or invalid structures. So what you do to test an entire argument translated into formal logic for its structure is what you do is you put all of the constituent statements up on top. You put all the constituent letters of any of the statements on the left side. And then you run through all possible combinations of the constituent letters. You calculate the values that gets for the premises and the conclusion. And what you are looking for is specifically this. If, when you are running through all the possible combinations of truth values, whether it's 4, 8, 16, 32, 64, or so on, if you can find even one set of values where every premise is true, but the conclusion is false, then you've proven that the argument is invalid. And you only need one. So here's a very simple argument with a very simple truth table. If D, then A, not D, therefore not A. If you look at the second set of truth values where D is false and A is true, you get the arrow statement true, you get the not D true, but you get the not A false. So when you see that pattern where you have a series of ones for the truth value of the premises, and then you have a 0 for the conclusion, you then have an invalid argument. If I were to say this argument in English, you would understand it would sound obviously wrong. The argument says something like this. If anything is a dog, then it must be an animal. But this is not a dog, therefore it must not be an animal. Now, obviously, there are things that aren't dogs, but are animals. So it's sort of obviously a bad argument. So what we do is we use the truth table to prove what's wrong with it. And what's wrong with it is on the situation when something fails to fulfill D, but does fulfill A, you will get the premise is true, but the conclusion will still be false. And that is the very definition of invalid. So what we're going to do from here is this. We are going to use truth tables to test entire arguments to see if the argument is valid or invalid. So you run through all the possible combinations. If there's even one, like the second one in bold, where all the premises are true but the conclusion is false, it's an invalid argument. If you run through all the possible combinations and there's no such situation where you get all the premises true but the conclusion false, then you have a valid argument. Now, the obvious danger with this method is going to be it's going to get very long, very complicated, very fast, right? I mean, because just look, we already have to run the values of 12 statements up there. And what happens if we get like 3 premises and a conclusion and 3 constituent letters, so you have to run 8 sets of values and not 4? I mean, you're going to get up to 24 and 30 tables with 24 and 32 spots very, very quickly. And that's a lot like work. And then you get things that, they're not going to be little simple things like not B and not A. But what if all the premises are complicated stuff like if P or not Q, then R? Well, what you need to do is this. You need to use shortcuts. And what the shortcut strategy lets you do is this. It is a way of ruling out sets of truth values. It's a way of recognizing quickly that some of them cannot give you an invalid set of values. So remember, the definition of invalidity is we have to have all premises false. I'm sorry, I said it wrong. We have to have all premises true, but the conclusion false. So if we get even one premise false, as soon as we realize that there's a false premise, we can just rule out that set of truth values because it's not going to result in an invalid set of values. So remember, we're looking for the magic combination where both these premises are true, are ones, but the conclusion is false, a 0. So the argument is if D, then A, D, therefore A. So on these first 2 set of values, as soon as you plug the value in for D, showing that premise 2 is false, you don't have to do the rest of the work for those sets of truth values. Why? Because you can just basically cross them out and say, no matter what we do, no matter what happens on those other 2 statements, it can't result in an invalid combination. Right? So you plug in the value for D first. You rule out having to do the rest of the work on set of values 1 and 2. For set of values 3, you plug it into the if-then statement, which gets you true on the left, false on the right, resulting in a false premise. So you don't have to figure out the conclusion. So here, you only have to figure out the all 3 of the statement values for this 4th value. And once you've figured that out, you realize that there's no situation where all the premises are true and the conclusion is false. Therefore, we've proven that the argument is valid. Does that make sense? So the goal here is to quickly rule out combinations of truth values as potential truth values that can give us an invalid combination. So here, I've written out anytime we identify a false premise, you can rule out the possibility that's going to give us a invalid set of values. It's also actually true anytime you recognize that you're going to have a true conclusion, then the argument cannot give you an invalid set of values. So you could, if you want to start with the conclusion and just plug in true for combination 2 and true for combination 4, you wouldn't have to calculate out the premises, because you cannot get all the premises true but the conclusion false when you already know the conclusion is true. All right, let me do one for you. Actually, I should do it where the camera is. All right. I am on 6.6a. If it rains and your tent leaks, then your down sleeping bag will get wet. If it rains, R, and if the tent leaks, L, then your down sleeping bag will get wet. That's statement 1. Statement 2, your tent won't leak, not L. Therefore, your down sleeping bag won't get wet. So we have R, L, and W. How many rows are we going to need? We're going to need 8. 2 times 2 times 2. So we start by alternating the truth values on the innermost variable, 0, 1, 0, 1, 0, 1, 0, 1. Then we'll double up, double 0, double 1, double 0, double 1. And then we'll do 4s. Now again, I don't want, so if I were to do this all the way out without any shortcuts, I would have to plug in 24 values, 8 times 3. That sounds like a lot of work. I'm kind of lazy. I got things to do with my life. I don't want to do that much work. So instead, I'm going to start with this simple premise, premise 2, not L, and I'm going to plug in the values in all 8 situations for not L. When L is false, not L is true. When L is true, not L is false. All right, so those are the 8 resulting 8 values for premise 2. Now I immediately see I have done half my work, because on values 3 and 4 and 7 and 8, we already have a false premise. And where we have a false premise, we cannot get all the premises true, but the conclusion false. So then I will X out the values of the rest of the statements in those 4 situations. And I'm halfway done. But I still don't want to do all the rest of the work, so let me look at the conclusion, not W. Let's plug in all the values for the conclusion. When W is false, not W is true. When W is true, not W is false. All right, now we can eliminate two more. We can eliminate set of values 1 and set of values 5. Because in those two situations, we know the conclusion has to be true. And if the conclusion is true, we cannot have an invalid set of values because we are not going to have the situation where all the premises are true, but the conclusion is false. So then I only have to calculate out this long premise for set of values 2 and 6. For a set of values 2, R and L are both false, making the and false, making the left side of the arrow false, making the arrow true. And for set of values 6, the R is true, the L is false. That makes the and false, which makes the left side of the arrow false, which makes the arrow true. And when we look at that, we realize, what have I just proven? I've proven that the argument is invalid because we have two sets of values where both premises are true, but the conclusion is false. But at least I did it without figuring out the values of all the statements and taking extra time. Does that make sense? All right, who would like to try one? Who would like to come up to the board, give it a shot, and work one of these? Yes, sir. Come on down. Do you have a particular one you'd like to do, or do you want me to assign you one? All right, you come on down and do 5. Excellent. So just put 5 over here, and we'll all watch as you kind of reason your way through it. Would you like me to hold the book for you? Yes, please. All right, so number 5 is, if I get Grand Canyon reservations and get a group together, then I'll explore canyons during spring break. That's the first statement. Right. Is that okay? Let's get you a better one. Let's throw this one. Good, so we got RT and E. So it's going to be R and T. Close parentheses, arrow, E. All right, then the next premises, I've got a group together. That's just T. And the next premises, I can't get Grand Canyon reservations, so it's not R. And the conclusion is I won't explore canyons, not E. Good. All right, set it. Yeah, so the easiest way is just alternate zeros and ones under that E. Go down 4 more. So do 0, 1, 0, 1 on, under the D. Good, then do, under the T, do double zeros there, and then double ones, and then do all ones. You're doing great. Fantastic. All right, so how are we going to do this in a lazy way with shortcuts?
I can do like either of these, and just to see if they end up doing.
So start with either the T, yeah, why don't you just start with that T? Plug in those values for T. Good, so we've got valuations 1 and 2, we have false T's, and 5 and 6. So good, we're halfway done already. Then do the not ours, great. Yep, you can just skip over. Good. Right. Good, so we're down to our final 2 sets of values, values 3 and 4. Why don't you take a look at that not E at the end. All right, so we see on value 3, we have a true conclusion. So that's not going to result in an invalid combination. So we only have to work that longer statement on set of values 4.
Yeah, this one, these two is that. So this.
That is correct. It is invalid because on value R false, T true, E true, it gives us all true premises but a false conclusion. So that's all you have to do. Simple, easy peasy. I mean, no, it's not. It's work, but it's not stuff that you can't do. Are there any remaining problems? We've got a few minutes. Any other problems from 6.6 that you would like to see me do? We're all supremely confident. All right, for next time, we're going to do 6.7, the truth assignment test. Have a happy Friday. That week went fast.
I can't believe I didn't realize that before, but those values are all increasing in binary.
Yes.
That was just a connection I'm surprised we didn't make till now.
Yeah. I mean, binary is based on logic. We're learning to think like computers. This is a mechanical method of running through all of our truth tables. If you had a classic like 1980s computer that worked really slow, you can see it work these out mechanically and slowly the way we're doing.
Yeah. One of my very first classes here was the Intro to Computing class in the department, in the physics PCSE department, and yeah, just brought me back to this.
Good. Very good.
I'll see you later, Dr. Silverman.
Thank you. You hang in.
I'll try.
How's it going for you?
I'm either going to be in 4 o'clock, this time I was a little pressed for time, so I'm able to. Definitely going to go back and do this one, because I'm a little bit confused, maybe. I don't know.
I mean, you'll definitely want to review it. Because this is, one of the skills that would be on exam 3.
Have a good weekend.
Thank you, you too.
Thank you.
Thank you very much.